We're going to look at a new concept called particular solutions and also apply this to finding velocity coming from position functions or acceleration functions using an antiderivative or an integral. So our first example, we want to find the integral of 2 over root x dx. First step is I need to rewrite this so I no longer have a fraction. So I'm going to bring up that root x as x to the negative 1/2. And then I can apply the rule where I add 1 to the exponent, divide by the new exponent. So basically that's like an anti-power rule for antiderivatives or integrals. So when I add 1 to the exponent, I now have x to the positive 1/2. I'm going to divide by 1/2. Well, dividing by 1/2 is the same thing as multiplying by 2. And then I still had this 2 in front as a coefficient. And then on all antiderivatives, we have to put plus c at the end, because at this point in time, we don't know if there was a constant being added or subtracted behind it. So when I take the derivative of this constant, it would go to 0. This derivative should give me the integrand on the inside of this integral. And then, of course, I can simplify this. So I end up with 4x to the 1/2 plus c. And that would be my solution for that integral. Our next example looks at finding the integral of t squared plus 1 quantity squared dt. So right now we are assuming we don't have an anti-chain rule, so I don't know how to actually integrate it when I have different layers with a composite function. So instead, I'm going to simplify this function by multiplying it together. So if I have t squared plus 1 being squared, that's the same thing as t squared plus 1 times t squared plus 1 dt. That allows me to FOIL it, so I end up with t to the 4th plus 2t squared plus 1 dt. And now that I have single terms, I can go through and individually take the integral of each term. So with my first term, I add 1 to the exponent, divide by the exponent. I get t to the 5th, divide by 5, plus the 2 remains as a coefficient in front. Add 1 to the exponent, so t cubed, divide by the new exponent, which is 3. And then keep in mind, inside this integrand, this is the derivative. I'm working backwards to the original function. So if 1 is my derivative, the antiderivative 1 would go to t, and then of course plus c behind it all. And that would be my solution. Now we have different types of solutions, which all depends upon what are we given in the problem. So if I am given what is called an initial condition, we are talking about a point that gives us the value of the function at one particular value of x. So when I talk about the value of the function, I'm talking about the y value at one particular of x. This is just a fancy way of saying we are given an x and y coordinate point that we can plug into our antiderivative to solve for the plus c. So I'm going to make a note here that when we're finding the initial condition, we use this to solve for that plus c in the antiderivative. With a particular solution, we actually have that c value from the antiderivative solve for the value that it actually equals. And so this gives us one particular answer, one specific answer. So this is a specific solution to a differential equation found by using the initial condition, which is that point that they gave us. If we do not have a point that's given, though, our antiderivative will have a plus c at the end. And so because c is a very generic number, we call that a general solution. So a general solution is just any solution to a differential equation, but it'll have plus c at the end. Okay, so for this next example, I want to find both a general solution and then turn around and find the particular solution. So the general solution, where f prime of x is equal to 1 over x squared, is just telling me I need to take the antiderivative, or the integral, of 1 over x squared dx. Well, that's a fraction, so I'm going to have to rewrite that with a negative exponent, so I can actually integrate it. When I integrate it, I get my answer is going to be negative x to the negative 1 plus c. So my general solution finds the original equation f of x, but we don't know what the original constant number is, so we have a plus c at the end. So what I have written in green is what we call the general solution. Now let's say we want to find the particular solution satisfying the initial condition f of 1 is equal to 0. Well, this tells me that I have the coordinate point 1, 0, and I'm going to use that x and y value to go back and plug it in to this general solution so I can actually solve for the value of c and then rewrite this equation with the c value actually plugged in. So this tells me that y is equal to 0 when x is equal to 1, so I have 0 is equal to negative 1 to the negative 1 plus c. So 0 equals negative 1 plus c, which means c is equal to positive 1. But we can't stop there. All we did was just find the constant value. So now I need to go back and plug that into the general solution, and the remaining function would be what we call the particular solution. So f of x is equal to negative x to negative 1 plus 1. That is my particular solution. So the difference between the particular and the general is the general solution has the generic constant c. The particular solution already has the specific value of c already plugged in, which came from the initial condition which was given in the problem. Now, there will be a lot of applications of particular solutions. The one we're going to focus on today would be the application where we relate it to physics, meaning specifically the position, velocity, and acceleration relationships. So earlier, you learned how to find position, velocity, acceleration using derivatives. Now we're going to eventually have to go backwards using an antiderivative. So here's our first problem. It says a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. So we have this building that is 80 feet tall, and the guy at the top of the building is throwing a ball upward. So it goes up and then it comes back down. And they tell me that the initial velocity is going to be 64 feet per second. Now all of this occurs at time equals 0, so if I wrote these out as points, position normally is given as s. So position at 0 seconds was 80 feet. The velocity at 0 seconds is positive 64 feet per second, and I know it's positive because the ball is going up, so velocity has to be positive. And based on all of that, I'm supposed to come up with the position function giving the height s as a function of t. So think about this for a moment. When we learned about position, velocity, and acceleration previously, we talked about how this forms basically a ladder. I have a YouTube video about this if you forgot any of these concepts. Going down the ladder, I take a derivative. So to go back up this ladder, so to go from acceleration to velocity to position, you have to take an antiderivative. Well, the problem is, if I'm trying to get to position, I don't have any other formula to begin with. So what I have to also consider is acceleration due to gravity. Acceleration due to gravity in feet per second squared is negative 32 feet per second squared, and that is a number we will need to memorize. Well, acceleration due to gravity is always a constant number, which means I can actually start with this function, work my way back up this ladder to position by taking 2 steps, which is going to be 2 antiderivatives. So if I start off with the antiderivative of acceleration in relation to time, so I have to write dt, that's going to be the integral of negative 32 dt. Well, that just goes back to negative 32t plus c. And so when I take the antiderivative of acceleration, I worked backwards a step, and now I'm at velocity. But before I can go back another step to get to position, I'm going to need to actually solve for that c value. So that's where I use this point right here. So when time is equal to 0, velocity was equal to 64, so c would equal 64. So if I rewrite that, velocity is equal to negative 32t plus 64. So now I need to go back another step to go from velocity back to position, which means I'm going to take the antiderivative of velocity with respect to time. So I'm integrating negative 32t plus 64 dt. Well, that goes back to negative 16t squared plus 64t plus c. And when I go backwards a step, I end up at position, which is s of t in terms of notation. But again, I have to find that c value, so this is where I'm going to use my first initial condition, which said that at time 0, the height was 80. So when height is 80 and time is 0, I end up with c is equal to 80. So now I can go ahead and move this up a little bit and rewrite position as a function of time with the c value plugged in. And so this would be the particular solution for position here. That's my answer. So now that I have the position function, I can calculate other things. So let's say I want to calculate when the ball hits the ground. Well, when the ball hits the ground, we know position has to equal 0. So my position formula we just found was negative 16t squared plus 64t plus 80. I can set that equal to 0 to solve for t. Well, notice I can factor out a negative 16, leaving me with t squared minus 4t minus 5. That does factor, so I get negative 16 times t minus 5, t plus 1. And solving that, I end up with t is 5 and negative 1. But of course I cannot have negative time, so I'm not going to include that answer. So my final answer is just at 5 seconds. So it'll take the ball 5 seconds to reach the ground after the guy throws the ball up from 80 feet. So for our final part, we want to calculate when does it reach the maximum height. Well, when the guy throws the ball up into the air and then it comes back down, in order for it to reach the maximum height, it has to hit the top of this parabola right here. And when that happens, it temporarily stops mid-air before it turns around and starts to fall back towards the ground. When it temporarily stops, velocity is equal to 0. So what I can do is take the velocity equation that we found in part A, where we found velocity was equal to negative 32t plus 64, and I can set that equal to 0 to solve for t. So this would give me t is equal to 2 seconds. That's when the ball will reach its maximum height. If I wanted to calculate what that height is, then I would just take 2 seconds and plug that into s of t, which is the position formula.